Everybody wants to go faster than light. Science fiction is full of it. Warp drives, hyperspace, jump gates. And when physicists say you can't, people assume we're being killjoys. Like there's some cosmic speed limit posted on a sign, and we're the ones enforcing it. That's not what's happening. The situation is considerably more interesting than that, and considerably more disturbing. Let me start with something concrete. You're sitting there reading this. You think you're stationary. You're not. You're moving at roughly 30 kilometers per second around the sun, which is itself moving at 220 kilometers per second around the galaxy. But set that aside. Relative to this room, you're sitting still. Now, what does faster than light even mean? You need to measure speeds relative to something. Relative to the room. Relative to another ship. Relative to what? This is already a question people skip over, and skipping it is why the confusion starts. In 1887, Michelson and Morley set up an interferometer in Cleveland, an instrument sensitive enough to detect differences in the speed of light depending on which direction it was traveling. The idea was simple. If light travels through some medium, the way sound travels through air, then our motion through that medium should make light appear faster or slower, depending on whether we're moving with it or against it. They looked for that difference. They didn't find one. Not approximately zero. Zero. That result was a catastrophe for the physics of the time. It meant light wasn't behaving like sound. It wasn't behaving like anything anyone had ever measured. Every other speed you've ever clocked depends on your reference frame. Throw a ball at 20 meters per second from a train moving at 30 meters per second, and someone standing on the platform measures the ball at 50 meters per second. That's just arithmetic. Light doesn't do that arithmetic. Measure light from a stationary source. You get 299,792,458 meters per second. Measure it from a source rocketing toward you at half that speed. You still get 299,792,458 meters per second. Measure it while you yourself are moving toward the source at 90% the speed of light. Same number. That's not intuitive. That's not a small effect. That's the universe telling you something structural about how space and time work, and Einstein in 1905 was the one who actually listened. What he said is this: the speed of light is the same for all observers because space and time are not absolute. They adjust, for every observer in exactly the right amount to keep that number constant. When you move faster, time runs slower for you. Not as a metaphor, not as a perception. Physically slower. Clocks tick at different rates. Distances actually compress along the direction of motion. These aren't hypothetical. We measure them. GPS satellites run their clocks deliberately offset by 38 microseconds per day, 45 microseconds gained from running in weaker gravity, minus 7 microseconds lost from moving fast, because if you didn't account for relativistic effects, GPS would drift by about 10 kilometers per day. Your phone finds your location because engineers took this seriously. So here's what's actually happening. As you approach the speed of light, your mass increases. Not feels heavier, increases. At 90% of light speed, your effective mass is about 2.3 times your rest mass. At 99%, it's about 7 times. At 9.9%, it's about 22 times. The relationship is not linear. It follows the Lorentz factor. Gamma equals 1, divided by the square root of 1 minus v squared over c squared. As v approaches c, gamma approaches infinity. What does that mean, operationally? It means the amount of energy you need to keep accelerating grows without limit. Not a large but finite amount. Without limit. To reach light speed, you would need infinite energy. That's not an engineering challenge. Infinite is not a number you overcome with better rockets. Now here's where people usually say, fine, you can't reach light speed. What about slightly below it? Or what if we skip space altogether? Wormholes, warp drives, something that doesn't involve actually moving through space at all. These are real proposals. Miguel Alcubierre in 1994 published a genuine solution to Einstein's field equations, the same equations that describe black holes, gravitational waves, the expansion of the universe, that describes a bubble of space contracting in front of a ship and expanding behind it. Inside the bubble, the ship is locally stationary. The bubble itself moves faster than light. You, inside the bubble, never personally exceed light speed. You just get carried. Sounds like a loophole. It isn't. Here's why. First, to create the Alcubierre bubble, you need something called exotic matter. Matter with negative energy density. Not matter with low energy, negative energy. The kind of stuff that, as far as we know, exists only as quantum fluctuations at extremely small scales, in amounts that are many orders of magnitude below what you'd need to fold spacetime around a spacecraft. Harold White at NASA spent years trying to minimize the energy requirements. His best estimate still came out requiring something like the mass energy of Jupiter in exotic matter for a modest bubble. We can't make exotic matter. We don't know if it can exist in macroscopic amounts. The Casimir effect shows quantum vacuum fluctuations can produce negative energy densities in tiny gaps between plates, but the total negative energy there is negligible. You're not warping spacetime with that, but even if you could build it, and let's be serious about what even if is carrying in that sentence, there's a deeper problem. It's the one that transforms this from an engineering question into a physics catastrophe. Special relativity has a feature that most people know but don't actually absorb. It says there is no universal now. Two events that appear simultaneous to one observer do not appear simultaneous to an observer moving relative to the first. This isn't a glitch or a perception issue. Simultaneity is genuinely observer-dependent, and the relationship between how different observers disagree about simultaneity is precisely determined. It goes as vt/cs squared, where v is the relative velocity between them, and t is the time separation. Here's what this implies. Suppose you have a faster-than-light signal. Doesn't matter how it's produced, wormhole, warp bubble, telepathy, whatever. Call it FTL. You send the signal from event A to event B, and in your reference frame, B happens after A. Fine. Now I switch to a reference frame moving at high velocity relative to you. Because of the relativity of simultaneity, in my frame those events swap order. Bad happened before A. Your signal traveled backward in time. This isn't a philosophical concern. The mathematics is exact. If you can send a signal FTL in any reference frame, then for some valid reference frames, and in special relativity, all inertial reference frames are equally valid. There's no preferred one. That's the whole point of the theory. That signal arrived before it was sent. And then, you can chain signals. Send FTL message from A to B. B sends FTL message back to before A was sent. The message arrives before you sent it. This is not a paradox in the sense of wow, strange. It's a paradox in the sense that causality, the rule that effects follow causes, is violated. You can receive an answer before you ask the question. You can kill your grandfather before your father was born, and not because of some contrived thought experiment, but because the math of spacetime guarantees it follows from FTL. Let me be careful here, because this is where people's intuitions mislead the most. You might say, okay, but in my frame, the sequence is fine, because before effect, why do other reference frames get to override what I see? Because in special relativity, there is no frame that's more real than another. The moving observer and the stationary observer are both correct about physics. If you send me a message FTL, I can find a valid reference frame where I reply before you sent it, and then chain that back, and you receive my reply before sending the original message in your own frame. The paradox comes home. This is not a feature of any particular model of FTL travel. Wormholes, tachyons, warp drives, they all have this problem because it's not about mechanism. It's about what faster-than-light communication means in a universe with the relativity of simultaneity. You can't have both. It's one or the other. Now, there's an obvious question sitting here. Quantum mechanics. Entanglement. Everybody's heard that when you measure one entangled particle, the other one instantly responds, no matter how far apart they are. Einstein called it spooky action at a distance and hated it. Experiments starting with Alain Aspect in 1982 confirmed it definitively. Measuring one particle of an entangled pair does affect the other one instantaneously across any distance. So isn't that FTL? No. And understanding why it isn't is one of the most important lessons in physics. When you measure your particle, you get a random result, spin up or spin down, for instance. Your colleague at the other end also gets a result. When you compare notes, you find the results are correlated in ways that couldn't have been arranged in advance. That's what Bell's theorem and Aspect's experiments showed. Ruling out so-called hidden variable theories, the correlations are real, non-local, and instantaneous. But here's the critical point. You cannot control what result you get. You flip the switch on your detector, and the particle gives you a random answer. Your colleague sees a correlated answer, but they don't know, before calling you, whether their answer is correlated or not. They just see their own random result. No information has moved between you. To transmit information, you need to be able to encode something, a message, a choice, a bit. With entanglement, you cannot encode a choice. The randomness prevents it. The correlations only become visible when you compare results through a classical, slower-than-light channel. This is not a technicality. It's fundamental. Quantum mechanics is in this specific sense conspiring to preserve causality. The non-locality is real, but informationally inert. No signal travels. Same thing with the quantum tunneling barrier traversal experiments in the 1990s. Gunther Nimtz and others measured what appeared to be faster-than-light transmission of a signal through a barrier. The peak of the wave packet appeared on the other side before it should have. But the peak of a wave packet is not information. To send information, you need the front of the wave, the leading edge that carries the news. Something is coming. That front edge never exceeded light speed. The peak position was misleading. This is subtle and worth sitting with. The group velocity of a wave can exceed c under certain conditions, but the signal velocity, the front velocity, does not. Claude Shannon's information theory, applied carefully, shows no information traveled FTL. So here's where we've arrived. The prohibition on faster-than-light travel is not a speed limit. It's the statement that causality and the relativity of simultaneity cannot coexist with FTL communication or travel. The universe, as far as we can tell, is structured so that the two things that would have to break are the things it absolutely refuses to break. Not because nature is conservative or cautious. It turns out the consistency of cause and effect, the fact that the past determines the future and not the other way around, might be deeply connected to why we can do physics at all. If effects could precede causes, the whole project of finding laws that predict the future from the present collapses. What remains unknown is genuinely interesting, not cosmetically interesting. We don't know whether the topology of spacetime permits stable wormholes at any scale. We don't know whether some theory of quantum gravity, string theory, loop quantum gravity, something nobody's thought of yet, changes the situation near the Planck scale of 10 to the minus 35 meters. We don't know if the universe has regions of spacetime connected in ways our current equations don't capture. We don't know what dark energy is, and dark energy is accelerating the expansion of the universe in ways that are pushing distant galaxies away from us faster than light, not as a violation of relativity, but as an expansion of the space between us, which is a genuinely different thing, but it shows the universe is comfortable doing things that look like FTL from the outside. What we do know is that anything achieving genuine FTL transportation or signaling in a universe with special relativity would enable time travel, and time travel, the kind where you go back and kill your grandfather or prevent your own birth, makes logic itself fail. Physics is built on consistent logic, so either special relativity is wrong in a very precise and specific way that has so far evaded every test we've run, including tests accurate to 1 part in 10 to the 22, or faster than light travel is not possible. The evidence for special relativity is not modest. Particle accelerators like the Large Hadron Collider at CERN accelerate protons to 99.9999991%, the speed of light, a Lorentz factor of about 7,500. The proton's mass increases exactly as predicted. Their internal clocks run slow exactly as predicted. Magnetic fields have to be tuned to account for the relativistic mass increase, or the beams would spiral out. The whole machine is an existence proof of special relativity, operating at enormous precision. When physicists say you cannot travel faster than light, they are not saying we've looked around and haven't found a way yet. They're saying if you could, then effects could precede causes, and that would mean the framework in which physics is done, logical consistency in time, is not a feature of the universe. Maybe it isn't. That's a real possibility. But then the theory that replaces special relativity needs to reproduce every measurement we've ever made that confirmed it, explain why causality appears to hold in all our experiments, and break down only in the regime of FTL in a way that somehow avoids the paradoxes. That would need to be a very precisely engineered failure of a very well-confirmed theory. The honest answer to can we travel faster than light is not in any universe that works the way ours appears to work. If you want to get somewhere far away fast, the interesting loophole is time dilation itself. At 99.9999% of the speed of light, your Lorentz factor is about 707. You could travel 707 light years and experience only 1 year of personal time. You're not getting there faster than light, but from your perspective, the distance has contracted by a factor of 707. The universe genuinely gets smaller for you. You can't outrace light, but you can, in some sense, outrace your own aging against cosmic distances. That's the universe's actual offer. It's not nothing.